Ooh, an HMMT problem. Number 8. Wow, you're in for a treat here. Let ABC be an acute triangle with circumcircle gamma. Let the internal angle bisector of angle BAC intersect BC and gamma at E and N, respectively. Let A prime be the antipode of A on gamma, and let V be the point where A prime intersects BC. Given that EV equals 6, A prime equals 7, A prime N equals 9, compute the radius of gamma. How to start, man? How are we going to start? Well, it's only two lines, two chavings here. Might be a bit approachable, maybe through a bash of some sort. No, yeah, of course, you could express, let's see, we can actually find the ratio of AV over AN through some tools, and then, yeah, okay, sorry, that was a bit vague. I'm not supposed to present that solution here, but it's doable. You can actually check the HMMT solutions. I'm sure there would be a non-inversion solution there. So let's get on with the inversion. First of all, the motivation of inversion is that we have an angle bisector here. We have a triangle ABC here also. And the diameter here makes it pretty straightforward also. But we're not going to invert through O, we're going to invert through A, because that's going to do some good things, some very good things with the angle bisector over here. So let's use our inversion tools. We're gonna invert through A with radius squared AB times AC and reflect over AN, or AE, same thing. And so we know that A, B, C will remain fixed. Let's start drawing here. Let's have a little more fun. I'm gonna change the color. Which color do you guys want? Let's use green. We have A, B, C here. And I'm actually going to draw in B prime and C prime here because a few of the observations I'm going to make might be a bit hard for you guys to intuitively understand. Oh god, I'm having another problem. Okay, so I'm going to draw. Oh, what? It's odd. There we go. B prime. And we're going to draw these points in because a few of the observations I'm going to make are a bit weird. You might not understand at first glance. So let's draw in our I think I messed yeah, so I'm gonna have to redraw this. No worries. A, B, C. We're gonna have our C prime here. And we're gonna have our B prime here. So let's draw A, B, C, the circumcircle. We can draw A prime, C prime. Don't worry, I'll erase it after so it won't look so complicated in the end. Let's go back here. So what's gonna happen to this point, A prime? Well, first of all, because A prime lies on circumcircle of ABC, when we invert, it's gonna end up on line BC because we were inverting through A. It's gonna end up on line B prime, C prime, sorry. So A prime will be somewhere on this line B prime C prime. I shouldn't. Let's say A prime prime, okay? So A prime prime should lie somewhere over here. Now, note that if we reflect over the angle bisector, we're going to have some isogonals. Isogonal is just the definition of reflecting over angle bisector. I'm just formalizing a little. So since A prime is the reflection of AO, A prime lies on AO, when we reflect over the angle bisector, it's going to lie on BC, right? Because C prime goes to B, B prime goes to C. And then because AO, it's well-known fact that AO and AH, where H is the orthocenter, are actually isogonal reflections over the angle bisector. So it turns out A prime is actually going to be the foot of A to BC. Isn't that interesting? Let's call this point HA. Oops. Okay. Now, similarly, we want to know where V goes. So V is line AO intersect BC. So now V prime is going to lie on the circumcircle, the arc of A prime, B prime, C prime. In other words, it's going to lie here. But similarly, we use that isogonal argument so that V prime's reflection over the angle bisector is going to lie on line AH, where H is the orthocenter. And it's also going to lie in the circumcircle of ABC. So we're going to draw that in here because this will be V's image. Let's call this point K. Now, alright, we also need to know where E and N go. We actually don't even need to know where O goes because we need the radius, but A prime is already a diameter. We can use that instead. So let's see. AN is going to be inverted to N is going to be inverted to E actually, because we can show that AB times AC is equal to AE times AN through similar triangles. Basically show that ABE is similar to triangle ANC, which is pretty clear because this angle is equal to this angle, and we have an angle bisector. So that's easy to show. So E is mapped to N. And in addition, since we're reflecting over the angle bisector, but this is the angle bisector, we're just staying on the same line. So N prime is going to be E, E prime is going to stay N. So, yeah. But in this inverted diagram, I'm actually just going to keep E and N their same names. Okay. Well, I'm going to draw that in after I erase this. Oops. My bad. Or I can just redraw it in. And we're also going to want to keep V and A prime. Okay. E, V, and A prime. Now, time to start using our distances. This is a computational problem. So, let's see. Let me get myself. Okay. What's going to happen is, okay, it may not look like it, but one very important thing you need to notice is that NA prime is equal to NK. Now, why this is true? Consider the orthocenter here. It's well known that K is the reflection of H over BC, and A prime is the reflection of H over the midpoint of BC over here. So by this we have some more similar triangles. Let's say M over here, HM, HA, A prime, projection over here, M. And then these are congruent triangles. So and then we have this reflection over here also. So it's pretty easy to note that NK equals NA prime, not too hard to prove. But yeah, so now we know NK is equal to, what is the length of NA prime? NA prime is 9, right? Yeah. So NK is 9. Now it's time to use our inversion distance formula. Let's go use NK as our, let's say we were trying to find NK. NK is equal to, we're going to go back to this formula. So NK equals R squared, but R squared is just AB times AC. And I'm having this problem. Alright. I'm really sorry if this is bothering you guys. I don't know what's happening, but just bear with it. So let's go back. Okay, so AB times AC, that's there. And then we want our denominator, which is center A, distance from A to N prime. What is N prime? Okay, so N prime was inverted to E under just the, from now on, we're just gonna, okay, so distances are gonna get a bit weird here, but because we're just reflecting over this angle bisector, distances are gonna be preserved. So that means, say we are considering A prime. We can model A prime off the distance of AH. Because AH, when we reflected it back over the angle bisector, which was the original image of A prime, that actually has the same distance, right? So since distances are preserved, we can just look at our distances here, right? As long as we're considering distances from only A. If we're not, things might just get weird. Or will it? We'll see. Let's see. Just because of this reflection, and this reflection shouldn't change too much about distances. So let's go back. AN prime. AN prime will be AE. And then AK prime will be let's see, AV, right? Because K prime, V are the images. I'm not gonna say inverses now because we had the reflection also. AV. And then we also need to do N prime, K prime. N prime, K prime will have the same length as E and V. Now, we can actually express AB times AC in a different way. Remember before we said that AB times AC is equal to AE times AN because ABE is similar to AN times AC, right? We're going to use that here. So AB times AC is equal to AE times AN. and this is actually really helpful because from now on, we either know the lengths in here in this equation, or we can substitute these lengths in terms of r. So AE cancels out. We're left with AN over AV times EV equals NK. But NK we said is 9. EV is 6. So 3 over 2 equals AN over AV. How are we going to express AN and AV though? Well, for AV, we haven't even used the 7th part yet. Since A prime is the diameter, A prime has length 2r, and VA prime has length 7. So AV has length 2r minus 7. And AN, what is AN? Well, look, A prime is a diameter, so angle ANA prime equals 90. But AN prime, A prime N, this is another helpful part of why we decided to invert. A prime N has length 9, A prime has length 2r, so we use Pythag. So AN has length root 4r squared minus 81. Now we have r, so we just solve. It looks like it's going to be a quadratic. Let's find out. 6r minus 21, we're cross multiplying, equals 2 root 4r squared minus 81. Squaring gives 36r squared minus 252r plus 441 equals 16r squared. 20r squared. This is after simplification. This looks like a terror to solve. I'm not sure why HMMT decided to make such big numbers in this quadratic, but after some trial and error, we find that this factors as 2r minus 15, 10r minus 51. Alright, so either r is equal to 15 over 2 or r is equal to 51 over 10. But note that our radius OA prime is actually greater than A prime V. So OA prime, or in other words, R is greater than 7. So we find that 15 over 2 is greater than 7, but 51 over 10 is not. So that means our only possible value is 15 over 2, and we found our answer, 15 over 2. Oh, that was something. Let's continue.